Let us continue alkali metals. In the alkali metals, we will see alkali metals in liquor ammonia. We will see. Now we will dissolve alkali metals in liquor ammonia and we will prepare concentrated solution. We are preparing concentrated solution. So, in concentrated solution, how alkali metal ions will be there along with the ammonia? In the sense, ammoniated metal ions. Here, metal ion present in the form of ammoniated metal ions. Electron present in the form of ammoniated electron. Ammoniated electron. These will be bounded. These will be bounded and it will look like metal lattice. So, first, how metal lattice will look, that we will see. Suppose we are taking sodium metal lattice. Sodium metal lattice we will take. Sodium metal piece we will take. Its crystal structure is a body-centered cubic. Now, sodium atoms will be arranged like this. Sodium atoms will be arranged like this in the sodium metal lattice. That arrangement is coming under body-centered cubic. That crystal structure is body-centered cubic. Like this arrangement will be there. Now, in the concentrated solution of alkali metal in liquor ammonia, how it will be there means, alkali metal will exist in the form of ammoniated metal ion and electron exist in the form of ammoniated electron. They will be packed in what manner means, here ammoniated metal ion, here ammoniated electron, next ammoniated metal ion, next ammoniated metal ion, next ammoniated electron, next ammoniated electron, next ammoniated electron, next ammoniated metal ion, next ammoniated electron. Like this, they will be packed. That means in the metal lattice, between metal atoms, ammoniated electron comes. Like that it is there. Therefore, we can call this is as expanded metal. Why we are calling this is as expanded metal? In the sense, between metal atoms, distance is raised. Between, this is one metal atom, this is one metal atom, between them distance is raised. Therefore, we will call them, this is as a expanded metal. Now, in this one, unpaired electron is absent. Therefore, we can say it is a diamagnetic. This concentrated solution is called a diamagnetic because no unpaired electron. That means here electron is there. When electron is there, how do we say no unpaired electron? And how do we say it is, how do we say no unpaired electron? Experimental analysis says that this solution is diamagnetic. That means unpaired electron should not be there. Unpaired electron should not be there in the sense, here we are writing one electron means we must write another electron here. It is clockwise means it is anti-clockwise. Like this we should represent. Then we can call this is as experimental. Then we can give that is a suitable explanation for experimental fact. Okay. So experiment says that it is a diamagnetic. Okay. Then it is this concentrated solution as a bronze color. Concentrated solution as bronze color. And this solution is metastable. What is metastable means it is stable for some time and then it decomposes or converted into some other thing. That is the meaning. Metastable means it is stable for some time and then converting into some other form. That is the meaning. Okay. It is converting into what form? That we'll see. That is it is converting into some other form in the sense it is stable or unstable. It is unstable. Okay. So it is converting into some other form. What is that? That we'll see. Now this metal ion we will take, this ammoniated metal ion we are taking, then this ammoniated electron we will consider, ammoniated electron. Now what happens means it is converting into metal amide. It is converting into metal amide, that is ammoniated, then hydrogen gas is liberated. That means here what is the reaction takes place means this electron is there, ammonia we will write like this. This nitrogen is having lone pair, this electron is attacking this H, this bond is shifting. Therefore, this H loses the electron here, gains the electron here, and becomes hydrogen atom that combines with another hydrogen atom and becomes hydrogen gas. It is this nitrogen gains this bond pair as lone pair, therefore it gets a negative charge NH2 minus. NH2 minus this M plus, therefore MNH2. It is called metal amide. We can call this is as metal amide. If we take sodium, we can call sodamide. If we take potassium, potassium amide, we can say. Okay. Now this alkali metal ion is converting into metal amide when in the sense when this solution is left for long time. That means left for long time in the sense leave this solution for sufficient time. What will happen in the sense it is metastable, it is stable for only certain time. After some time it is converting into, this solution is converting into metal amide. Even dilute solution also converting into metal amide on long standing. Then another condition is if catalytic impurity is present, then also this alkali metal with ammonia gives a so and so. If a anhydrous condition not there, hydrated condition is there, water molecules are there, then also like this decomposition is possible. Therefore, like this reaction is possible when in the sense when the solution is left for long time. Which solution? This concentrated solution or dilute solution. So like this reaction is possible when the solution is left for long time. Next, presence of catalytic impurities allows this reaction. Next, if any water molecules are there, then also this reaction is possible. Okay. So we have discussed about alkali metals in liquor ammonia. We have discussed in this one. Next, we will go for alkali metal carbonates. Next, we are going for alkali metal carbonates. Now, regarding carbonates, alkali metal carbonates are soluble in water. Alkali metal carbonates are soluble in water. Rest of all the metal carbonates are insoluble in water. So in the carbonates, in the metal carbonates, only alkali metal carbonates are soluble in water. Remaining all the metal carbonates are insoluble in water. So now we are saying that alkali metal carbonates are soluble in water, we said. Down the group, what happens to the solubility? That we will see. Down the group, solubility of alkali metal carbonates. Down the group, solubility of alkali metal carbonates increases. Okay. It is experimental fact. Okay. So down the group, solubility of alkali metal carbonates, what happens means increases. Okay. In the previous class, we have seen down the group solubility of alkali metal hydroxides we have seen. Down the group solubility of alkali metal hydroxides we have seen. How that solubility is there? What we said, solubility of alkali metal hydroxides increases. That's what we said. So alkali metal hydroxides solubility also down the group increases, we said. Now how to explain this fact? That we'll see. Down the group solubility of alkali metal carbonates increases. This how to explain, we'll see. Solubility in the sense two factors playing a role. One is lattice enthalpy. Another one is hydration enthalpy. Another one is hydration enthalpy. Down the group, size of cation, radius of cation increases. Therefore, what happens to the lattice enthalpy? Lattice enthalpy is directly proportional to charge of cation into charge of anion by radius of cation plus radius of anion. Down the group, radius of cation increases. Therefore, lattice enthalpy decreases. Okay, lattice enthalpy decreases. Lattice enthalpy decreases in the sense solubility should increase. Solubility should increase. Because lattice enthalpy is endothermic in the solubility case. Endothermic, that magnitude of endothermic nature decreases means solubility will rise. Then hydration enthalpy will see. Hydration is based on radius. So down the group, radius of cation increases. Extent of hydration decreases. Therefore, hydration enthalpy decreases. It is exothermic reaction. Hydration enthalpy is exothermic. Hydration enthalpy is exothermic, we can say. So, hydration enthalpy decreases in the sense exothermic nature decreases, therefore solubility will decrease down the group. So, hydration enthalpy says solubility like this, lattice enthalpy says solubility like this. What experiment says means experiment says like this. So, as per experiment, the dominant factor is this one. This is not dominant factor. So, down the group, lattice enthalpy decreases, therefore solubility increases. It is the dominant factor in this case. That means decrease in lattice enthalpy is a dominant when compared to decrease in hydration enthalpy, therefore solubility increases. Okay. Then stability of alkali metal carbonates will see. Alkali metal carbonates are thermally stable. Alkali metal carbonates are stable, we can say. So down the group, what happens to the thermal stability? Down the group, how the thermal stability will be there? Down the group, thermal stability increases. Down the group of alkali metal carbonates, thermal stability increases. Why is it so? Now, we can say lithium carbonate, we will take lithium carbonate, alkali metal carbonate, lithium carbonate will take. This on heating decomposes to give lithium oxide and carbon dioxide. All the metal carbonates decomposes to give metal oxide and carbon dioxide. Metal oxide on further decomposition gives metal and oxygen for silver and mercury. In this one, exception is there. Sodium carbonate, potassium carbonate, rubidium carbonate, cesium carbonate do not undergo decomposition. This on heating, these carbonates do not undergo decomposition. They will reach their melting point, then they will start melting, but not undergoing decomposition, even at red hot condition. So, in the alkali metal carbonates, lithium carbonate decomposes like magnesium, which is a diagonal relationship, but sodium, potassium, rubidium, cesium metal carbonates do not undergo decomposition on heating. So, this itself indicates that down the group thermal stability increases. Thermal in the sense heating. Stability in the sense, though heated, it is not going for any change, it is stable. That's what thermal stability says. So down the group thermal stability increases. That means lithium carbonate decomposes easily as like magnesium, with they as diagonal relationship, whereas sodium, potassium, rubidium and cesium carbonates do not undergo decomposition on heating. Okay. Next. Next, bicarbonates will take. Bicarbonates we have taken. Alkali metal bicarbonates. Alkali metal bicarbonates exist in solid state. We can prepare alkali metal bicarbonates in the solid state, except what? In the sense lithium bicarbonate. Lithium bicarbonate exists only in aqueous solution but not in solid state. We cannot prepare solid lithium bicarbonate, but remaining alkali metal bicarbonate, sodium, potassium, rubidium, cesium bicarbonates can be prepared in solid state. Solid alkali metal bicarbonates we can prepare. Lithium bicarbonate we cannot prepare in solid state. Lithium bicarbonate exists only in aqueous solution. What about rest of the metal bicarbonates? Alkaline earth metal bicarbonates, D block metal bicarbonates, P block metal bicarbonates. All the metal bicarbonates exist only in aqueous solution. Any metal bicarbonate you take, that will exist only in aqueous solution. But sodium, potassium, rubidium, cesium bicarbonate can exist in solid state. So, which metal bicarbonates exist in solid state? Sodium, potassium, rubidium, cesium alone. Lithium and other metal bicarbonates exist only in aqueous solution. Sorry. Next, bicarbonates on heating. What will happen means carbonate, water, carbon dioxide will be obtained. Any bicarbonate you take, alkali metal bicarbonate or alkaline earth metal bicarbonate, any metal bicarbonate you take, that will decompose to give carbonate, water and carbon dioxide. Say, for example, we will take sodium bicarbonate. Sodium bicarbonate on heating gives what means sodium carbonate, water and carbon dioxide. So whatever the metal bicarbonate you take, any metal bicarbonate on thermal heating, that decomposes to give metal carbonate, water and carbon dioxide. Now, down the group, what happens to the thermal stability of alkali metal bicarbonates? We'll see. Down the group, thermal stability increases. Down the group, thermal stability of alkali metal bicarbonates increases. Okay. Next, solubility, we'll see. Alkali metal bicarbonates are quite soluble in water. Alkali metal bicarbonates are quite soluble in water. We know baking soda. Baking soda is sodium bicarbonate that exists in solid state. We can dissolve that one in water, that we know that. Okay. Next, we will take nitrates. We are taking what in the sense nitrates we are taking. Now we will take alkali metal nitrates. We are taking alkali metal nitrates. This alkali metal nitrates on heating gives alkali metal nitrite. On strong heating gives alkali metal oxide. On strong heating gives alkali metal oxide. Okay, example we will see. Sodium nitrate on heating to 500 degrees Celsius, we are getting sodium nitrite and oxygen. This on further heating, that means heating to 800 degrees Celsius. What happens means giving metal oxide, NO2 and O2. So, sodium nitrate on heating to 500 degrees Celsius gives sodium nitrite and oxygen. On heating further, this decomposes to give sodium oxide, NO2, O2. So, lithium nitrate on heating gives directly lithium oxide, NO2 and O2. Lithium is the exception. So, which is coming under this category in the sense sodium, potassium, rubidium, cesium. Okay. So, regarding nitrates like this. Generally, if you see nitrates on heating, that gives metal oxide, NO2 and O2. It is general. Generally, metal nitrates on heating gives metal oxide, NO2 and O2. It is a general thing. Okay. Next, we'll see manufacture of sodium. So now we will see manufacture of sodium by which method, in the sense Dow's method. Down's method. We are going for Down's process. In this process, we will manufacture sodium. We will manufacture sodium from molten sodium chloride. From molten sodium chloride, we are manufactured. By which method, in the sense electrolysis method. Why we have to go for electrolysis method means alkali metals are quite reactive. Alkali metals we cannot expose to atmospheric air since it is quite reactive. So we cannot prepare alkali metal by chemical method. By chemical method we cannot prepare. Only by electrolysis we can prepare alkali metal. Okay. So now we will go for electrolysis. Electrolysis, in the sense we have to take anode. We have to take, what is the anode we are taking here, in the sense we are taking graphite anode. That graphite anode we are taking in this form. So this is a graphite anode. It is connected to positive charge. It is graphite. It is anode. Okay. Next, we are taking steel as cathode. Steel as cathode. Okay. That steel cathode we will keep here. This is steel, which is cathode. Steel cathode we are keeping here. Steel cathode. How many steel cathodes we have placed, in the sense only one steel cathode we have placed, which is cylinder, which is like cylinder. This steel cathode is cylinder. Inside this steel cathode cylinder, this graphite anode is there. This is a steel cathode. This is steel cathode. It is steel cathode. It is not two steel cathodes, so only one. This steel cathode is in the form of cylinder. Inside that, this graphite anode is there. Next, what is taken, in the sense diaphragm is taken. Next, diaphragm is taken, that is placed here. This is what, in the sense a diaphragm. This one is a diaphragm. What is the necessity of diaphragm, in the sense due to diaphragm, anodic product and cathodic product cannot mingle with each other, cannot mix with each other. Due to diaphragm, anodic product and cathodic product cannot mix with each other, cannot come in contact. Okay. Then here a dome arrangement is placed. Dome arrangement is placed. It is just like a dome. Dome arrangement is placed here. Next, we are taking the electrolyte. Electrolyte we are taking. What is the electrolyte here? Electrolyte is a sodium chloride and calcium chloride. Sodium chloride 40%, calcium chloride 60%. This is taken in which form, in the sense molten form. Molten form we have taken. To keep this one in molten state, we have to provide the necessary temperature. The necessary temperature is how much, means 1123 Kelvin temperature is provided. 1123 Kelvin temperature is provided here. Okay. So this is the electrolyte. Now this vessel is closed. This vessel is a closed vessel. In closed this vessel, after taking this electrolyte, we are closing this vessel. Okay, the vessel is closed. Here we are leaving some gap. Later we will say why is it so. Okay, now you think that it is closed vessel. Now it is taken for electrolysis. Current is passed. It is going for electrolysis. At anode, what happens? At anode, what happens? Anode means anion goes to the anode. What is the anion? Cl minus. Cl minus goes to this anode. So Cl minus goes to the anode. At anode, oxidation is possible. So it is losing the electron. Then it becomes chlorine atom. Chlorine atom combines with another chlorine atom and becomes chlorine gas. That chlorine gas is liberated at this place. Chlorine gas is obtained at this anode, which is coming out like this. Chlorine gas is coming out like this. At anode, chlorine gas is coming out. Next, we will see cathode. At cathode, what happens? At cathode, what is the reaction takes place? That we will see. So, cation will go to the cathode. What is the cation? One is sodium ion, another one is calcium ion. Sodium ion is there, calcium ion is there. Now, sodium ion goes to the cathode. Sodium ion goes to the cathode and takes electron and becomes what in the sense sodium. Sodium ion goes to the cathode and takes electron and becomes sodium. Now, at this cathode, what is obtained in the sense sodium is obtained. Okay. So, here at cathode, which goes to the cathode means sodium goes to the cathode and becomes sodium. That sodium is obtained at this cathode. That sodium is in the molten form. Sodium is in which form? In the sense molten form. That molten sodium is having density lesser than this electrolyte. Therefore, the molten sodium moves up. That is moving up in the sense we are keeping an arrangement like this. We are keeping an arrangement like this. In this one, what is taken in the sense kerosene is taken. In this one, kerosene is taken. It is filled with kerosene. Now, at this cathode, sodium is produced, which is in molten state, which has a density lesser than this electrolyte. Therefore, the produced molten sodium moves up and comes like this, and that will be collected under the kerosene. So we are getting a sodium at this place. Sodium at this place we got. Okay. Here, what is the necessity of calcium chloride? Why we have to add calcium chloride in the sense? Sodium chloride is the ionic compound. That melting point we want to decrease. For that case, calcium chloride is added. So we added calcium chloride in order to reduce the melting point of this sodium chloride. So to reduce the melting point of sodium chloride, we are adding calcium chloride. Even potassium chloride also will be added in order to reduce this melting point. So we are adding other substances, this calcium chloride or potassium chloride or potassium fluoride in order to reduce this melting point. Okay. So we are reducing this melting point by adding this one. So sodium goes to the cathode for cathodic reduction. So we got sodium at this place, and we are collecting the sodium under the kerosene we are collecting. Okay. This process is called Downs process. In this Downs process, we are manufacturing sodium from sodium chloride. Okay. Next, we will go for a manufacture of sodium hydroxide. We are going for manufacture of sodium hydroxide. That sodium hydroxide we are manufacturing using which method? In the sense Kastner-Kellner cell or mercury cathode cell. Okay. Now we are taking a Kastner-Kellner cell. Otherwise, mercury cathode cell. Mercury cathode cell. Mercury cathode cell. Okay. How this arrangement, how the arrangement will be there here, that we will see. In this one, we are taking, this is also by electrolysis only. Here we are taking a anode. Anode is what in the sense graphite. Here we are taking the anode. Anode is what means graphite. So this is anode. This is what means graphite. Okay, anode is like this arrangement is taken. Then we are taking electrolyte. So we are taking electrolyte here. What is the electrolyte? Electrolyte is a brine solution. So that electrolyte we are taking in this vessel. So here we are introducing brine solution here. That brine solution in the sense aqueous solution of sodium chloride. Aqueous solution of sodium chloride. Okay, so aqueous solution of sodium chloride acting as the electrolyte. So if any excess of sodium chloride is there, if any excess of sodium chloride is there, that will come out like this. That will come out like this. So aqueous solution of sodium chloride we have taken here. Next, we will take cathode. What is the cathode here? Cathode is what means like this. Cathode will be like this. Will be. This cathode is what in the sense moving mercury is acting as cathode. So mercury is moving like this. Mercury is flowing like this. Moving mercury is acting as cathode. So this here how the arrangement will be there means mercury can flow easily like that arrangement we have to keep here. So moving mercury will flow like this. Mercury will go on flow like this. That moving mercury is acted as cathode here. Sir, okay. Now we are passing the current here. So electrolysis is taking place at anode. What is happening here at anode? Which is going to anodic process. Which is going to anodic process means Cl minus goes to the anode. At this anode, Cl minus goes. That Cl minus becomes a chlorine atom by losing electrons. That chlorine atom combines with another chlorine atom and becomes chlorine gas. So we are collecting chlorine gas here. Chlorine gas we are collecting here. Okay, so chlorine is produced here. That chlorine gas we are getting at this place. That means here brine solution is coming. That up to this level brine solution will come up to this level. Then over that means it will come out. Therefore, this place is vacant place. At this place, what will produce in the sense, what will come in the sense, chlorine gas will come. That chlorine gas will escape like this, will come out like this. So at anode, we are getting chlorine. That chlorine we are collecting here. Sir, now we will see cathode. At cathode, what is happening? At cathode, what is happening in the sense, sodium ion goes to the cathode and becomes sodium. That sodium mixes with mercury and becomes sodium amalgam. Sodium amalgam, we can say. So we got sodium amalgam at cathode. Okay, at cathode we got sodium amalgam. The obtained sodium amalgam, we got sodium amalgam here. This sodium amalgam is allowed to run into water. So sodium amalgam is allowed to run into water. So what happens means sodium reacts with water and becomes sodium hydroxide, and in water, from water hydrogen gas is liberated. Mercury is getting separated. Mercury is getting separated. Okay, so sodium amalgam reacting with the water and becomes sodium hydroxide and hydrogen gas. So water becomes what? The sodium becomes what? Sodium is losing the electron and becomes Na plus. Sodium is losing the electron and becomes Na plus. In water, this electron is attacking the water. Sodium is giving electron, that electron is attacking the water hydrogen. This bond is shifting. So this OH becomes hydroxide and sodium and hydroxide becomes sodium hydroxide. This hydrogen atom losing the electron from this bond and gaining the electron here and becomes hydrogen atom, that becomes hydrogen gas here. We got hydrogen gas at this place. Then mercury is detached. So we got what in the sense sodium hydroxide we got. This method is called Costner-Kellner cell. Here mercury is acting as cathode. Therefore, we are calling this is as a mercury cathode cell. Mercury cathode cell we can say. In this process, this cathode is what in the sense mercury. That mercury becomes sodium amalgam and we are collecting here, that is run into water in order to get sodium hydroxide. Here itself water is available, no? Here itself water is available. Then why sodium is not reacting with this water? If sodium is reacting with this water, we might have got sodium hydroxide here, no? Because here it is cathode. At cathode, water will not come for reaction. So sodium ion goes to this cathode and becomes sodium. That obtained sodium immediately should come out. That should not stay here because that will react with water. So that should come out immediately. Therefore, only we have arranged here moving mercury. If sodium is staying here, that will react with water, no doubt. If sodium is staying here, that will react with water. So sodium should not be stayed here. Therefore, only slope arrangement is placed. As soon as sodium is produced, that is going out immediately. But we said sodium is quite reactive with water. Sodium is quite reactive with water in the sense, as soon as sodium obtained here, that would have reacted with water, isn't it? But it is not reactive. Why? Because sodium is in the form of sodium amalgam. Sodium amalgam in the sense, sodium reactivity is less when compared with pure sodium cell. Next, we'll go for next method. Diaphragm cell. We are going for diaphragm cell. We are going for diaphragm cell. Another method is called Nelson cell. Another method is called Nelson cell. Okay. In the Nelson cell, how to prepare sodium hydroxide, that we will see. Using Nelson cell, we are preparing sodium hydroxide. This is also electrolysis method only. Sir, in this electrolysis method, let us prepare sodium hydroxide. Now we will take anode. Anode is graphite here. It is anode. It is graphite. Next, we will take what in the sense cathode. We will take the cathode is what means wire gauze act as cathode. This wire gauze act as cathode. Wire gauze. It is having many holes. This is made up of many holes. Wire gauze. Wire gauze means it is a metal sheet, iron metal sheet. It is made up of many holes. This is wire gauze act as a cathode. Then anode and cathode are separated by asbestos diaphragm. Anode and cathode are separated by a diaphragm. This is what in the sense asbestos. This asbestos act as diaphragm. Next, we will take electrolyte.